Hello students, welcome to the course on analog and digital communication systems, and the course code is EC501. This is the course for BTech 5th semester EC students. Myself, Dr. Surojit Bosak, Assistant Professor of EC Department, Guru Nanak Institute of Technology, Kolkata, and this is my official email address. In the last class, we have started a bandwidth efficient or bandwidth conserving modulation system, which is called quadrature phase shift keying, or abbreviated as Qpsk. And we have completed the mathematical expression, signal space diagram, time domain waveform, and probability of error of Qpsk. And now today we will discuss about the power spectra of Qpsk, generation and detection of coherent Qpsk, offset Qpsk and versus non-offset Qpsk, and M-ary PSK. So let us start lecture number 4 from the module 5, that is digital modulation techniques. And the today's topic is generation and detection of coherent Qpsk, power spectra of Qpsk signal, offset versus non-offset Qpsk, M-ary PSK. And the lesson objective of this course or of this topic is study various digital modulation techniques that can compute the bit error performance and compare their advantages and limitations. And the second lesson objective is study signal vector representation of various digitally modulated signals by creating signal constellation. And this topic is mapped with CO number 2 and CO number 5. So let us start lecture number 4 from the module 5, that is digital modulation techniques, with the topic of Qpsk. First, I want to give you a brief recapitulation of our last class. In the last class, we have started the Qpsk or quadrature phase shift keying. In Qpsk, which is basically a bandwidth conserving scheme. So in Qpsk, the phase of the carrier takes one of 4 equally spaced values, such as pi by 4, 3 pi by 4, 5 pi by 4, 7 pi by 4. And correspondingly, we have discussed on the mathematical expression of Qpsk signal, which is square root of 2e by t cos 2 pi fct plus 2i minus 1 into pi by 4, where I is equal to 1, 2, 3, 4, where E is the transmitted signal energy per symbol, and each possible value of the phase corresponds to a unique die bit. For example, we may choose the set it is like a gray encoded set of die bits. Say 10, 00, 01 and 11. So only single bit change from one die bit to next. And correspondingly, we have drawn the signal space diagram of 4 symbols, that is 10, 00, 01 and 11. And all, say, first point is pi by 4, then message point M2, phase difference of message point M2 is 3 pi by 4, phase difference of message point M3 is 5 pi by 4, and phase difference of message point M4 is 7 pi by 4. And correspondingly, we also get coordinates of the message points. And after that, we have discussed the time domain waveform, how a time domain waveform can be generated from a input binary data like that, say 0, 1, 1, 0, 1, 0, 0, 1. So what was the case? First, we generate odd number sequence, that is SI1 phi 1t. After that, we can generate SI2 phi 2t, that is even number of sequence. And ultimately, the Qpsk waveform is the sum of these two, that is SI1 phi 1t plus SI2 phi 2t. That means if two bits are changing, that is in the first die bit, first die bit 0, 1, second die bit 1, 0. So if two bits are changing, then the phase difference is pi. And if one bit is changing, then the phase difference is pi by 2. And there may be a chance that there may be no phase change or no bit change. In that case, no phase change. And ultimately, from this signal space diagram, we found earlier signal space diagram, we found that the error probability, which is same as the error probability of Qpsk signal. Up to this part, already we discussed in the last class. Just I give you a brief recapitulation of our earlier class. Now today we start from generation of coherent Qpsk signal. This is the block diagram for generation of a Qpsk transmitter or typical Qpsk signal. The incoming binary data is first transformed into polar form by a non-return to zero level encoder. Thus, symbol 1 and symbol 0 are represented by plus root over EB and minus root over EB. Next, the binary wave is next divided by a demultiplexer into two separate binary waves consisting of odd and even number of bits. And these two binary waves are denoted by A1t and A2t. We note that in any signaling interval, the amplitudes of A1t and A2t equal to, in our earlier waveform, it is like that, SI1 and SI2 respectively, depending on the particular die bit that is being actually transmitted. The two binary waves A1t and A2t are used to modulate a pair of quadrature carrier, or it is called orthonormal basis function phi 1t and phi 2t, where phi 1t is equal to square root of 2 by t cos 2 pi fct, and phi 2t is equal to square root of 2 by t sin 2 pi fct. The result is a pair of binary, because here from here you can generate a binary PSK signal, BPSK signal, and from here we can also generate a BPSK signal. And finally, two BPSK signal are added to produce the desired QPSK signal. So this is the generation techniques of coherent QPSK signal. Next is the detection or demodulation of coherent QPSK signal. The QPSK receiver consists of a pair of correlators with a common input and supplied with a locally generated pair of coherent reference signals phi 1t and phi 2t, which is shown in the figure. The correlator outputs x1 and x2 produced in response to the received signal xt are each compared with a threshold of 0. If x1 greater than 0, then a decision is made in favor of symbol 1 for the in-phase channel output. But if x1 less than 0, a decision is made in favor of symbol 0. Similarly, if x2 greater than 0, a decision is made in favor of symbol 1 for the quadrature channel output. But if x2 less than 0, a decision is made in favor of symbol 0. Finally, these two binary sequences at the in-phase and quadrature channel outputs are combined in a multiplexer to produce the original binary sequence at the transmitter input with the minimum probability of symbol error in an AWGN channel. So this is the in-phase channel and this is actually the quadrature channel. So this is how we can remodulate a coherent QPSK signal. Next is the spectrum or bandwidth or power spectra of QPSK signal. You know that in QPSK, a bit exists actually 2-bit interval. So depending on the die bit sent during the signaling interval, say t equal to minus TB2 plus TB, the in-phase components equal say plus GT or minus GT. Similarly, for the quadrature component and similarly for the quadrature component also. So these two valid for both in-phase component and quadrature component. So the GT actually denotes the symbol shaping function, which is denoted as say square root of E by T if T belongs to 0 to capital T, otherwise it is 0. Therefore, the in-phase and quadrature components are statistically independent Therefore, according the baseband power spectral density of the Qpsk signal, which is equals to the sum of individual power spectral densities of the in-phase and quadrature component. So, which is basically, it is a polar energy, that is spectrum of the polar energy waveform, that is a square TB into sin square FTB. So that here basically it is a square into TB, a square, that means 2E into TB, T cancel. So it is 2E sin square FT. So we know that E is equal to 2 into EB, beat energy, where E is the transmitted signal energy per symbol and EB is the signal energy per beat. So E is equal to, you know that E is equal to 2EB, so which is 4EB sin square 2, and similarly T equal to 2TB, so 2TB into F. So the bandwidth is half. See the normalized frequency FTB, just we Qpsk, the bandwidth is 0.5, and we will discuss the bandwidth of MSK a little bit later. Now I will show you the bandwidth of BPSK system. Okay. Just now I will show you what was the bandwidth of BPSK system. Now see the bandwidth of QPSK here. See the bandwidth of BPSK system. It was just cutoff point is 1, 2, but in QPSK it is 0.5 and 1. See the difference. So bandwidth is half. Here the bandwidth is 2 EB, but here 4 EB sin square FTB. So the bandwidth is just half. See the bandwidth, which is basically QPSK is cut point 0.5 and 1. So the bandwidth of QPSK is just half of the bandwidth of BPSK system. Okay. Now, a very few observations from QPSK constellation diagram, and from where we can see a offset type of QPSK, and that first see the observation. Actually, this is the non-offset type of QPSK. See, the carrier phase change by plus minus 180 degree whenever both the in-phase and quadrature components of the QPSK signal changes sign. An example of this situation is illustrated in this figure. When the input binary sequence switches from die bit 0, 1, see this is 0, 1 to 1, 0. This is, then there is a phase shift of either plus 180 degree, plus 180 degree. Now another observation is the carrier phase change by plus minus 90 degree. When? Whenever the in-phase or quadrature component changes sign. Not both, either in-phase or quadrature, but in case of plus minus 180-degree phase shift, both in phase and quadrature component should change sign. See, 0, 1 to 1, 0, both bit are changing. But the carrier phase change is plus minus 90 degree when only either in phase or quadrature component changes sign. Example, say when the input binary sequence switches from die bit 1 0 to die bit 0 0. So only one bit are changing. In this case, the in phase component changes sign, whereas the quadrature component is unchanged. And this is the second observation. And what is the third observation? The first observation is there may be a chance to phase shift of plus minus 180 degree. Second observation, there may be a chance of phase shift of plus minus 90 degree. Now, what is the third observation? The carrier phase is unchanged. Not necessarily there may be a phase change. Even there may be a chance to phase unchanged. When neither, which condition? When neither the in phase component nor the quadrature component changes its sign. So which is the case? When die bit 1 0 is transmitted in two successive symbols. That was actually observed in the when we draw the time domain waveform of Qpsk signal in the last class. So situation 1 to a much lesser extent. Situation 2 can be of a particular concern when the Qpsk signal is filtered during the course of transmission. And specifically, the 180 degree and 90 degree shifts in carrier phase can result in change in the carrier amplitude, thereby causing additional symbol error in detection. Now, the extent of amplitude fluctuations exhibited by Qpsk signals may be reduced by using offset Qpsk. So this first diagram is the non-offset Qpsk, and second diagram is the offset Qpsk, in which only we are allowing plus minus 90 degree phase change, or even there may be a chance to no phase change. But in offset Qpsk does not allow the plus minus 180 degree phase shift. Now the question is, which has the less error probability? Offset Qpsk or non-offset Qpsk? Obviously, the answer is offset Qpsk has less error probability compared to the non-offset Qpsk. Why? In case of offset Qpsk, we are not allowing 2-bit error. Plus minus 180 degree phase shift is not allowed. That means 2-bit changing are not allowed. So only there is a provision of 1 bit error maximum. Maximum chances of error probability in 1 bit error. So obviously it has a less error probability. Which was also calculated in the last class when we have determined the error probability of Qpsk signal. Next is the pi by 4 shifted Qpsk. An ordinary Qpsk signal may reside in either one of the two commonly used constellation diagram, which is basically a square constellation diagram shown in the earlier slide. See, in this slide, it's a square constellation diagram, or even this form, just pi by 4 shifted Qpsk. So this is the 8 possible phase states for the pi by 4 shifted Qpsk modulator. Just 8 possible symbols with 8 possible. So this green points are the earlier one, and now this one, and blue message points are the earlier for square constellation. So within these 8 possible phase states for the pi by 4 shifted Qpsk is shown here. So this is all about Qpsk signal. Now I am going and too much in depth, little bit depth, which is another type of PSK modulation scheme, which is called M-ary PSK. Actually, the concept of M-ary PSK comes from, actually, first is the BPSK. BPSK means we lump together 1 bit, just 1 bit transmitted at a time where there is a phase shift of 180 degree. Now in Qpsk, we lump together 2 bits and the bandwidth is half. See, the bandwidth is just reduced half. Now from that point, one question arises in our mind that if you lump together n number of bits, then is there any chances to reduce the bandwidth by an amount, by a less amount which is divided by, say, n? So from that concept, we think about another modulation scheme, which is actually advanced version of Qpsk, which is called M-ary PSK. Here we can say that Qpsk is a special case of M-ary PSK, where the phase of the carrier takes on one of m possible values, namely, say theta I equal to 2 into I minus 1 into pi by m, where I is equal to 1 to m. Accordingly, during each signaling interval of duration t, one of the m possible signals say SIT, which is say square root of 2e by t cos 2 pi fct plus 2 pi by m into I minus 1, where I is equal to 1 to m. Here E is the signal energy per symbol or per bit. And the carrier frequency Fc is equal to Nc by T for some fixed integer Nc. Now, what is the constellation diagram for this M-ary PSK signal? So, to draw the constellation diagram, first you have to think how many numbers of basis function are present. Naturally, from this earlier expression, we can see that there are mainly same two basis functions which was defined as phi1t and phi2t, similar to Qpsk, are needed. Now the signal constellation of M-ary PSK is therefore two-dimensional. The M message points are equally spaced in a circle whose radius is square root of E and center at the origin, which is illustrated here for the case of octaphase shift king. Octaphase shift king. That means M equal to 8. Number of message points are 8. So from this figure, we note that the signal space diagram is circularly symmetric. Now the question is, how from here, how can we determine the probability of error? Suppose that the ratio E by N0 is large enough to consider the nearest two message points, see, one on either side of M1 as potential candidates for being taken for M1 due to channel noise. Say this is for the case of M equal to 8, same case. And the Euclidean distance of each of these two message points from M1 is M equal to 8. Therefore, D12, that is the distance from M1 to M2, D12 equal to D18, which is determined as just angle, this is the decision boundary. So this angle is pi by m and this is the 90 degree perpendicular. So D12 equal to D18 equal to 2 square root of E sine pi by m. And correspondingly, the average probability of symbol error for coherent M-ary PSK is denoted as PE, which is ERFC square root of E by N0 sine pi by m. So this is the probability of error for coherent M-ary PSK. Next is the power spectrum of M-ary PSK. The symbol duration of M-ary PSK is defined as T equal to TB log M base 2, where TB is the bit duration. Proceeding in a manner similar to that described for a Qpsk signal, we may show that the baseband power spectral density of an M-ary PSK signal is given by 2E sync square Ft, which is 2 into EB log M base 2 sync square. Just this part is applying T equal to TB log M2 sync square TB F log M2. So naturally, by this expression, you can easily draw the spectrum of M-ary PSK. Now for M equal to 8, the bandwidth is smallest among these 2, 4 and 8. And the largest bandwidth is for M equal to 2. So this is all about M-ary PSK signal. Next, I come a problem regarding Qpsk. Very interesting problem. Let PEI and PEQ denote the probabilities of symbol errors for the in-phase and quadrature channels of a narrowband digital communication system. Show that the average probability of symbol error for the overall system is given by this PE equal to PEI plus PEQ minus PEI into PEQ. Again, I am repeating the problem. It's very interesting problem. Let PEI and PEQ denote the probability of symbol error for in-phase channel and quadrature channel. And you have to prove that the average probability of symbol error for the overall system is given by this. So how to prove this? Just first find out, see the solution. Let PEI is the average probability of symbol error in the in-phase channel, same, and PEQ is the average probability of symbol error for the quadrature channel. Now first we have to find out the correct decision of both in-phase and quadrature channel and their individual outputs. As their individual outputs for the in-phase and quadrature channel are statistically independent, they are independent. So the overall average probability of correct decision is 1 minus PEI into 1 minus PEQ, as they are statistically independent and their probability of correct decision is this. Just I multiplied it. Therefore, the overall average probability of error is 1 minus probability of correct decision. So this is PEQ plus PEI minus PEI into PEQ. So it is basically as their outputs are statistically independent, so their total average probability of error is 1 minus probability of correct decision. That is the product of 1 minus PEI into 1 minus PEQ. So in that way, you can easily prove the problem. So let us stop here. This is all about QPSK. Hope you understand clearly. So I stop here. Thank you. Thank you so much. And now I am ending my today's session.